Hey guys, so this is the first video I have on my restriction mapping tutorial, because I know there's not many sources out there for learning how to do restriction mapping. Like the farthest they ever go is a double digest, and what Gardner wants us to do in class is actually technically a triple digest, which requires an extra step that's pretty hard that we never really went into in depth. So the first step in any restriction mapping problem is to figure out what kind of DNA you're actually working with. Are you working with circular DNA or linear DNA? So the reason why this is important is just to figure out if your maps are going to be a circle or a line. So if it's linear, it's going to be a line, and if it's a circular plasmid, it'll be a circle. So in this example, it's going to be a circular plasmid. Sometimes it doesn't say circular, it just says plasmid. Just know that if it just says plasmid, it's going to be circle. So the first thing we're going to do is draw single digests. So single digests are restriction maps that only involve one enzyme. So the three right here are single digests. And then a double digest is with only two enzymes. And then eventually we want to get our full digest or our triple digest, because usually we work with three and we want to have a map with all three. So first you're going to start with your single digest. Then using those you'll make your double digest, and using the double digest you'll make your final one. So first we want to look at how many cuts each enzyme makes. So we know that BST1, it has 1 and 2 numbers. So that means it makes 2 cuts, because in a circular plasmid, if there's 2 numbers, that means it's 2 cuts. If it's a linear piece of DNA, 2 numbers would mean 1 cut, because there's 1 extra fragment. But I'll just keep it just as circles for now. So B makes 2 cuts, Eco makes 2 cuts, and N makes 2 cuts. So our final digest is going to have 5 cuts in total, which will be pretty important information later on. So let's just first make the single digest of BST1. Single digest BST1. So the two numbers that we have, or the fragment sizes we have, are 1800 and 2500. Let's draw our circle. And so we have 2 numbers, so we're going to have 2 cuts. These little dashes will represent our cuts. So the sizing of how far apart these little dashes are is important, because you want it to correspond to the number that you're working with. So we're working with 1800 and 2500, and as you could see, 2500 is a lot bigger than 1800. So we're going to want to make sure we have a section that's bigger than the other, but not a little too big. So this area right here is going to be 2500, and this area right here is going to be 1800. And before we want to do anything, we want to label our cuts with the enzyme that's actually cutting there. So that's going to be BS1, oops, wrong number, 1800, and this is going to be 2500. So that's our single digest already done for BSC1. I'm just going to check it off right here. The next one we're going to do is Eco. Eco also has 2 cuts. As you can see, it has 2 numbers. However, the contrast between these numbers is a lot larger than the one in BST1. So we want to make sure that this little 825 fragment has, the dashes are a lot closer to each other. So we have 1 cut right there and another cut, label it E. And then we have 825 for that small cut right here. And this larger part is going to be 3475. And we're already done with our single digest of Eco. So the next one we have is Engo, which only has 1 cut because it has 1 number. And what's interesting about single digest with only 1 cut is that number is going to be the entire length of the plasmid, which is important because we have to put the entire length of the plasmid in the middle of the restriction map. So I'm going to do that right now. And for ENGO, you could put the cut anywhere you want. You could put here, you could put here, 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 here. It doesn't matter because anywhere you cut once on that circle, it's still always going to give you a line that's equal to 3400. So we're just going to draw our cut right here, label it ENGO, and the total will be 4,300. Okay, nice. So these are all our single digests. We're going to be using these to create our double digest. So as you can see, the next one we have is B plus E. So this is our first double digest. And as you can see, it's the largest one because it has the most amount of cuts. It has 4 cuts in total, so we want to make sure that we have 2 cuts that belong to BST1 and 2 cuts that belong to ECO. And we know that that from the single digest. Right here, B has only 2 numbers and ECO has 2 numbers, so together they have 4 cuts, which is really useful because when we make our final digest, we want to use this one because it'll only be 1 cut away from the final one. But you'll see what I mean in just a moment. So let's go start on our double digests. We have BST1 plus ECO R1. And the numbers we're going to be working with is 300, 525, 1275, and 2200. So we have 4 fragments, and these are the sizes of those fragments. Let's draw a circle. This is our plasmid. Now we're going to be using one of these single digests to figure out the double digest. So we could either use the BST1 single digest, which is right here, or you could use the ECO one right here. So I'm going to personally start with BST1. So we're literally just going to copy that single digest onto our double digest. So first cut right here, BST1, and then another cut right here, BST1, 800 and 2500. So we know this had 4 cuts in total, and we just made 2 cuts, so there's 2 more cuts left. And we also know that B has 2 cuts in total, so we already used up all the B that we can. And we have 2 cuts left that need to be done by E. So let's figure out what numbers add up to 800, 1800 and 2500 in this little box right here. So as you can see, 525 and 1275, they equal 1800 right here. So we can actually cut that piece into, when we cut this piece, you want to just label it instantly so you don't lose track of what enzyme you're working with. So this is going to be ECO, and we're going to be using 525. Why did this turn into a line? 525, and I'm going to change that into 1275. The reason why is just because that piece we were working with, 1800, we're splitting that into 2 pieces. So now this piece right here is going to be 1275, and this piece over here is going to be 525. It's going to be cut by E. These 2 sides will be B. I'm just going to erase this real quick. And then now we made another cut, so we have 1 more cut left. that needs to be done by eco. So we could just add up the numbers that we didn't use. Since we already used 525 and 1275, we could take 300 and 2200. If you add those together, it conveniently adds up to 2500. So you could just split that with eco, because we had one more cut left that needed to be done with eco, -1. We're all done with this. We just need to change our numbers, because that 2500 got split into 2200 and 300. We're also going to write that total plasmid length in the middle. Alright, so let's do the second double digest next. So that one's going to be with eco and engo. The numbers we're going to be using are 800, 825, and let's see, what is that? 2675. Okay, so let's use the single digest with the most cuts. So as we could see, engo only had one cut, so that's not going to be as useful to us as eco, which has 2 cuts. And also, as you could see, this 825 is also right here. So we could draw this again over here the same way. So we're going to make a cut by eco like this, and another cut by eco like this, and write 825, and then we have this big 3075 piece right here. And we want to be able to split that because we have these 2 numbers left that we need to use. And that cut is going to be done by engo, since eco did all of its work already. It did its 2 cuts that it already did in its single digest, so we're just going to make a cut with engo. So engo is going to make a cut here, or it could be here. It just has to be the correct size. This is going to be 800, cut by n. And then this bigger piece right here is going to be worth 2675. Because 800 plus 2675 equals 3475 over here. So we're already done with our eco and engo digest. So the next one we have is B plus N. BST1 and engo MI. These are the size of the fragments we're going to be using is 1100, 1400, and 1800. Going to draw a circle. And let's use the B single digest to make this double digest, since it has more cuts than the engo single digest. It has 1800 and 2500, which is convenient because we see 1800 here and 1800 here, so we could already cross that off. So let's draw in our B cuts. So here's the B cut from the single digest. B cut from the single digest, the 1800. We used up 1800, and there was a 2500 right here. And if we add up 1100, I didn't mean to erase that. Okay, if we add up 1100 and 1400, that equals 2500. So we can split this 2500 into 1100 and 1400. Let's do that real quick. And we're going to use engo to do that. Alright, so this double digest is already done too. So the last thing we're going to do is our final digest. So we're going to be using, again, the double digest with the most amount of cuts, which is going to be let's see. This one has 4 cuts, this one has 3 cuts, and this one has 3 cuts. So we're going to work with this one right here, the one with B plus E. So let's just copy this one onto this one. We had a cut with B right here, and this fragment size was worth $12.75. There was a cut by Eco right here, a cut by B, and then another cut by Eco, and then we have this large portion that is equal to 2,200. So we knew from earlier that we needed 5 total cuts, and this digest only involves B and E, so we're missing N. So we had 5 total cuts that we need. We had 2 cuts done by E already, that's done, and then we had 2 cuts done by B. So we have one more cut needed by N, because N only does 1 cut. So let's see where that could go. So the easiest way for me to figure out where this cut would land is to look at the double digest with N go. So I like to add up some numbers in this area that has N go and just see if these numbers that can add up to these, because that means that a combination of these numbers is something that a number up here can be split into. Let's see. $1,400 plus $825. This is where you just guess and check and just try to find a combination of numbers that work and add up to any of the numbers up there. Okay, so I just added up a bunch of random numbers, and I found out that 1,400 and 800 equal 2,200. So we can chop up this large big piece over here into 800 and 1,400. And just remind yourself that a large piece isn't always the one that gets cut. It could have been like 300. But 2,200 was a common number that was found in this case. So let's split that with N. We're going to have a 800 piece and this 1,400 piece right here. So this is going to be our final digest. And usually at the end, I just highlight all the fragment sizes. And as I can see, there's 5 total fragment sizes. And then I also do a red highlight. And all the enzymes, there's 5 enzymes, so 5 cuts. So I know that in a circular plasmid, 5 cuts equals 5 fragments.